All right. Well, greetings, everyone, and welcome to this special event called the James Webb Space Telescope Community Event. This is sponsored by NASA, and we are one of hundreds of sites around the country that are putting on special programs, both virtually as well as in museums and science centers and universities. So we're very excited here at the Delta College Planetarium in Bay City, Michigan, to be able to host one of these events. And today we're very fortunate to have a guest speaker. His name is Dr. Michael Meyer from the University of Michigan in Ann Arbor. And just to give you a little bit of an introduction to Michael, he's been at the University of Michigan since 2016. Originally from Missouri, he studied in Massachusetts and did research at the Max Planck Institute for Astronomy in Germany before moving to the Steward Observatory at the University of Arizona in 1997. He was a professor in the Department of Astronomy there until 2009, when he moved to the Swiss Institute for Science Technology in Zurich, Switzerland. And I love this part. In his spare time, he likes to tell awful dad jokes. I do that too, by the way. Tries to impress his wife with mediocre watercolor paintings and does a lot of laundry for the guinea pigs. And I can relate to that too. I have a lot of pets as well. So with all that set up, thank you, Dr. Meyer, and I'm going to turn it over to you.
All right, Mike, thank you very much for that introduction and for organizing today's event and participating in the James Webb Space Telescope community events. I'm thrilled to be here and looking forward to telling you a little bit about the James Webb Space Telescope and the excitement around it in these days leading up to what we hope will be a successful and flawless launch. The theme I'm going to focus on today is discovery space. And what I mean by that is the parts of parameter space that are opened up whenever we turn on a new capability or a new piece of technology. So there's a limit of what we could do before, and when we turn on something new, a whole new range of things opens up to us, and that we refer to as the discovery space. The Hubble Space Telescope has been in orbit and taking data from its perch above the Earth for a long time, since 1990. And it's quite aged, and it's feeling its age. Sometimes it has minor troubles and we can help it along, but eventually we will lose the Hubble Space Telescope. It's lasted far beyond its expected lifetime. And so the question arose, really even within a decade of launching Hubble, what will come next? What should be the next big thing? Hubble has explored star-forming galaxies, pushed back our vision to the early phases of the universe, studied forming stars and planets, but clearly we will want to take bolder and bigger steps into the future. And that led in the mid-90s to a series of high-level reports from commissions, internal NASA studies, and in the scientific community of what the next big thing might be after Hubble. And in those days, we referred to this as the next generation space telescope. I was very fortunate as a young scientist in the late 90s to be involved in a committee that was studying the kinds of cameras and spectrographs that should be on this facility and what its capabilities might be. And I'm not sure you can see my cursor, but there's a much younger and lower mass me perched in amongst these distinguished scientists there in the background. The James Webb Space Telescope will have incredible sensitivity compared to the observations we can do from the ground. In the top right, I'm showing the transmission of light through the Earth's atmosphere to the ground. And the blue is the percent transmission all across the electromagnetic spectrum, from the visible rainbow wavelengths we can see with the human eye at the far left, all the way out into what we call the thermal infrared at wavelengths of 10 times the reddest thing your eye can see and beyond. And you can see also there are big gaps in between these blue wedges, And these gaps are not places where we can see through the atmosphere. We must go into space. And the reason those areas are blocked are because of molecules in the Earth's atmosphere. And it's exactly some of those molecules that we would like to study in space. So you can see the markings at the bottom of all of these molecules. Water is H2O, carbon dioxide, CO2, and ozone, O3, and molecular oxygen, O2. All of these things we would like to study, but we can't because of Earth's atmosphere. So going above helps a lot. We can do some of this work from the ground in these blue wedges from high, dry mountaintops. But on the left-hand side, what is being plotted is the level of background noise, the glare of everything in our Earth's atmosphere and around us that is providing distracting light that prevents us from seeing what we want to see. The red dots at the bottom are that background glare in space, and the black line is what we have from the highest mountaintops on Earth. So in space, it's 1,000,000 times quieter and more faint to see against the background. And this gives us tremendous additional sensitivity by going into space. And these are the main two reasons why we must go into space. Well, the James Webb Space Telescope is truly one giant leap forward for space astrophysicists. And it's really a worldwide operation led by NASA, but we also have partners from the Canadian Space Agency and the European Space Agency who have contributed significant, important pieces to this global mission. There are at least 10,000 people spread out around the world in many different countries and in hundreds of institutes and companies who have contributed to fabricating pieces and design work for this giant space telescope. And so we're very, very excited to be getting awfully close to the launch. Well, let me just give a couple of rundowns of the major features of the James Webb Space Telescope, and I'll start on the right with the mirror size. There's a little figure of a person at the far left of this inset. And in the middle, you can see the circular area of the Hubble Space Telescope. It's a substantial, powerful space telescope that primarily works at the wavelengths that we can see with our human eye. The James Webb Space Telescope mirror is significantly larger by comparison. It has a diameter of 6.5 meters instead of 2.4 meters, and 5 times the collecting area of the Hubble Space Telescope. At the bottom, again, for referring back to the electromagnetic spectrum, the James Webb picks up at the reddest things your eye can see and goes many, many times farther into the infrared, out to 28.5 microns. And that's a 1/1,000,000th of a meter is 1 micron, redder than the reddest thing your eye can see. The orbit of the James Webb is also remarkable. As you can see on the middle left, it is orbiting one of the special gravitational points in the Earth-Sun system called L2, the Lagrange 2 point. There are 5 stable Lagrange points in the Sun-Earth system, and we will be with James Webb at L2 on the other side from the sun relative to the Earth. And it's quite a distant way out there, as you'll see in just a moment. One of the unique features of the James Webb being an infrared telescope is that it must be cooled, and that gives us this extra special sensitivity. So there's basically an umbrella or a layer of 5 sunshades that protect the telescope cold side from the sun pointing other side, and we refer to them as the hot side and the cold side. Almost a 600-degree temperature difference between the hot side and the cold side. And that's the remarkable insulation. You can think of it as SPF several million between the hot side and the cold side of that sunlight. So the telescope and all the instrumentation is being shielded from the sunlight. And on the back side, we have to dump all of that heat, but we also use that sunlight to power the spacecraft and observatory. Well, this whole behemoth is folded up like an origami, and stuck into the nose cone of an Ariane 5 launch vehicle. This spacecraft will be launched from French Guiana at a place called Kourou. And I just checked before this event today. There was some small delay from December 22nd to December 24th because of a communications issue, and that's been resolved. And so we're really on target for a Christmas Eve launch. And so I just hope that Santa and his sleigh can stay out of the lane of this space telescope as it's going into space for the first time. The mirror itself has to fold up all the instruments, the sunshade, everything into this compact configuration you can see in this image. I'm now going to show you a slightly over 2 minutes long video of all the things that are going to happen after launch. And I like to refer to this as the 28 days of terror. Some of you will remember the Mars Perseverance lander craft that went in July of 2020, where the descent and landing onto the surface of Mars was called 7 minutes of terror. But the James Webb is a much more complicated system, and it will take over 4 weeks for all of its components to be unfurled, put into position, reach their operating temperature, and for us to begin to operate the observatory. Literally, it will take a month before we know that everything is working. So you'll see this clock go in a very nonlinear fashion, jumping around days, hours, and minutes, and you'll see some description of some of the major events as we go through launch. So launch vehicle separation happens really fast. And then within about 30 minutes or so, that solar panel needs to come out. There's a battery that can operate it for a while, but we want to get that power from the sun sooner rather than later. There are a couple of initial mid-course corrections that you'll see in these first hours and days. That's to push the James Webb onto its way towards L2. Of course, it's important to maintain communications. Now we're up at day 2 and that another mid-course correction burn occurs. This is about where the Apollo 13 mission was in terms of its distance from the Earth. And you can see on the lower left, the spacecraft moving away from the Earth-Moon system. So now some more dramatic things are starting to happen. The sunshade, it's called, is being splayed out. It's about the size of a tennis court. And then a little tower has to push the telescope up to make room for the sunshade to spread out. These very fine membranes, about 1/1000th of an inch, covered with very reflective aluminum coating. And you'll see in a while, they'll have to fully extend themselves and become tensioned. Here, one of the booms on one side goes out, and then the boom on the other side to start to stretch out this umbrella that needs to protect the telescope from the sun. We tighten it up on all of the corners, and then all 5 layers need to be separated. It's just like your grandparents told you in the Michigan winter to wear layers, because each layer traps half of the heat going up or coming out, and multiple layers can provide multiple factors of 2 insulation against the sun. So now we're starting to see the telescope be deployed, the secondary mirror that bounces the light from the primary back through a hole in the primary to where all the cameras are behind the mirror. And now the mirror itself, the 2 flaps on each side, have to be deployed to fill out that 6.5 meter diameter aperture. Now, there's another important mid-course correction. You see we're at 29 days now, and we're just beginning to orbit the L2 position. It's a mostly stable orbit, but slight adjustments in position will need to be done to keep the James Webb Space Telescope hovering at that L2 point, far away from the Earth-Moon system, opposite the sun from where the Earth is positioned. So it's an extraordinary series of hundreds of maneuvers that need to happen just so. And the time between each of these that takes so long is often you will need to wait until 2 components that come into contact together for the first time will take many hours, if not days, to equilibrate in temperature before the next step can be made in the process. So it is an incredible technological achievement for this system to work and function properly. Well, that may make you wonder, how on earth do we know that all of these bits and pieces are going to come together? I sometimes myself get a little nervous when I see the video of that deployment. Rest assured, however, that hundreds and hundreds of engineers have tested each subsystem very thoroughly at each stage of integration. And that's really what the last several years have been. You test one thing, you test another, you put it together, you test the whole thing together as a subsystem, put that into another, test that subsystem, and so on until you get to the full observatory. This whole monstrosity was actually wheeled into a chamber that is evacuated and can be made as cold as we can in a chamber that size here on Earth. And if any of you are aficionados of the Apollo program, you might recognize this thermal vac chamber at Johnson Space Center in Houston, where much of the Apollo spacecraft was tested down there in this world's largest thermal vac chamber, meaning it can get evacuated and then cool down to the temperatures of space. One can never be 100% sure, but we're as sure as we can be after all of that testing that things will work well. Again, the James Webb Space Telescope is focusing on the infrared, again, redder than the reddest thing that your eye can see. And what sorts of astrophysics can one do in the infrared that can't be done at visible wavelengths that your human eye can see? Well, we can study cold things, because things like the temperatures of planets and even the temperature of our own Earth, the temperature gives a spectrum associated with that temperature that peaks at a wavelength of 10 microns, far redder than what your eye can see. So seeing cold things requires that you look into the infrared. It's also the case that dust in our Milky Way galaxy and throughout the universe preferentially blocks out blue light. And so just like sometimes it's hard to see on a smoggy day or to see through a fireplace smokestack as the smoke is billowing out, seeing through the dust in the infrared is a very important thing that James Webb can do uniquely. And in this middle image, you're looking at a picture of a disk of gas and dust around a very young star, which has been blotted out in the very center. And in this particular case, there's a planet a few times the mass of Jupiter forming just off of the center of this young star. So seeing cold things and being able to pierce through interstellar dust is a very valuable feature of the James Webb Space Telescope. And finally, perhaps the reason why the whole project was kicked off in the first place is that as you go look back at very, very distant objects, which because of the light travel time means you're really looking back in time, as the universe expands, the space between us and those objects expands as well. And the wavelengths of light that are passing between us and a very distant early universe object are being stretched out. And that means they are seen only in the infrared. So if we wanted to see the visible light of galaxies back in the early phases of the universe, when those galaxies were just forming, the billions of years that light has taken to reach us has stretched out that light, meaning we can only see it in the infrared. And sometimes the James Webb Space Telescope is referred to as the first light machine, meaning we can see back to phases of the universe within 100 million years and hopefully catch a glimpse of the very first stars, the very first galaxies, and the very first black holes that formed in the early universe. We will get for the first time a look at those objects in the infrared with the sensitivity of James Webb. So to illustrate that dust penetrating power, I like to show this lovely image of from the Hubble Space Telescope of the Eagle Nebula. You're seeing here the dark shadow of dust cast against the bright glowing background of hot gases, which are created by the high energy ionizing radiation of very, very massive stars. So as that blue light is streaming towards us, it gets blocked by these columns, sometimes called the pillars of creation, because there are tiny little infrared stars embedded all throughout this cloud of gas and dust, which is where stars like the sun formed and the planetary systems around them. So we're investigating really our birth origins by studying these very young stars and planets forming. And when I hit the next button, we'll transfer into the infrared, where you'll be able to see the scene change dramatically, and you'll be able to see hundreds and hundreds of stars throughout the frame, but in particular through these columns of dust, which were relatively opaque before. Well, now I come to explaining a little bit about each of the instruments. There are 4 main cameras and spectrographs of the James Webb Space Telescope, and I'm showing all 4 of them relative to the wavelengths of light that they can observe. 3 of them, the NIRISS, the NIRSPEC, and the NIRCam, only operate from 1 to 5 microns, and the MIRI, the real mid-infrared heat camera, operates from 5 to 25 microns. I've had the good fortune to be involved in 2 of these instrument teams over the last 20 plus years, and that's the NIRISS camera, which is being led by the Canadian Space Agency and my colleagues in Montreal, and also NIRCam. I have a long association with the colleagues at the University of Arizona who built this. And in fact, my boss on this project, Marcia Ricci, a very renowned infrared astronomer and mentor to me when I taught at U of A some years ago, she is a Michigander herself. She went to school and grew up here in Michigan in Midland, and ended up becoming a professor and a leader in infrared astronomy and building this camera for the James Webb Space Telescope. And I'm very honored to be working under her leadership for this project. So again, these are the series of cameras and spectrographs now compacted into something we call the ISM, the Instrument Science Module. And all 4 are packed in a different configuration, NIRCam on the lower left and NIRISS on the upper right. Cameras take pictures, not unlike your phone, at different wavelengths and using different detector technology, but we take digital pictures of objects in the sky and then analyze the light with our computer programs here on Earth. Spectrographs break up the light we see into the tiny little chunks of the spectrum, the individual wavelengths, so that we can see the fingerprints of different atoms and molecules in the absorption and emission spectra of different objects in the universe. And this telescope also has some specialized instruments to, believe it or not, block out starlight. One of the things that we want to do with the James Webb is to see planets around nearby stars and try to understand whether those planetary systems could be like our own. But that requires us blocking out the central star, because it's kind of like seeing a firefly near a large spotlight at a car dealership. If you turn the spotlight off, you might have a chance. But if the firefly is flying around the spotlight, it is extremely difficult to see the firefly. And that's kind of like what it's like to see planets around very bright stars. So we have specialized optics that are designed to block out the lights of bright stars so that we can see faint things extremely nearby them. The ability to fineness of detail for James Webb to take pictures is something like to be able to see the details on a penny if it were to be located 25 miles away from you. That's the fineness of detail that the optics of James Webb should allow us to see. Well, now I'm going to give you a brief tour of some of the main science cases that have excited the international astronomical community in deploying and utilizing the powerful capabilities of the James Webb Telescope. And one of them is transit spectroscopy. The first planet around a normal star like the sun was discovered in 1995 using the spectroscopic radial velocity method. This is really like the Doppler shift, the same thing where you can hear a siren coming and the pitch gets higher as it comes towards you, and then as the siren moves away from you, the pitch lowers. That is the same principle used in measuring the response of a star to a planet going around it, and it began the planet revolution, which we are still living through today, finding many thousands of planets around stars in our Milky Way galaxy and placing our own solar system in context. When a planet passes in front of a star, it can dim the light by a tiniest little fraction over time. And the dip that we see is proportional to the radius of that planet, so that big planets make a big dip and tiny planets make a tiny dip. Telescopes that we've used have been able to measure about 10 parts in a million of that dip as a tiny Earth-like planet moves in front of a star like the sun. And James Webb will be able to do this, not just in the white light curves, but also spectroscopically, breaking up these transit signals, these shadow signals, into each wavelength individually that allows us to actually detect molecules in the atmospheres of these planets. So I'm highlighting one system here in the lower right because it was a dramatic discovery about 5 years ago to find a system of 7 planets around an object that isn't even really a star. It is so low mass, about 10 times lower mass than our own sun, it can only barely sustain a handful of nuclear reactions in its core, and so it's not really glowing bright like a star like the sun. This tiny, dim, feeble star has a system of rocky planets around it, these 7, and the star we refer to as the TRAPPIST-1 star, and the planets are labeled B, C, D, E, F, G, and H, and they are, each one of them is slightly farther away than the interior one. There are some that appear to be in the liquid water zone of that dim, feeble light from that star, and in particular, this planet E here should have about the same surface temperature as our own Earth does. It's much closer to its star because its star is faint and our sun is much brighter. So we are out orbiting at the distance of the Earth from the sun. But we will be able to measure molecules in the atmosphere, such as are shown on the left. Carbon dioxide, if it's present, water vapor, if it's present, methane, if it's present, and be able to diagnose the atmospheric constituents on these planets. These are basically greenhouse gases, and we'll be able to detect these greenhouse gases in the atmospheres of such a planet. Some people think that if we worked really, really hard, devoting huge amounts of James Webb time to studying planets like this, maybe, just maybe, in 1 or 2 very favorable objects, we could even look for signs of life in the atmospheres of those planets. I want to stress, though, that that is not the major discoveries that James Webb will make, because it's extremely difficult and not even clear that we can get a good answer to whether there could be a habitable planet or not. So moving on to studying the formation of stars and planets, I showed this picture before of the uninspiring name PDS-70. It has 2 protoplanets embedded in the gas and dust-rich disk of material. Again, we've blocked out the light of the star with this artificial dark spot in the center, and this is the disk of gas and dust in the outer zone, the outer circle, and a little protoplanet here forming in the interior. We'll be able to study objects like the sun, very, very low mass stars that dominate the number count of stars in the galaxy, the most common kinds of stars, planets like Jupiter, brown dwarfs, these so-called failed stars, and other kinds of objects that form in these environments. We'll be able to study clouds of gas and dust in space and their dynamic interactions with the energetic radiation around them. We'll also be able to study black holes. We won't see the light from the black hole, of course, because that is the definition of a black hole, that even light can't escape its gravitational potential. But we'll be able to understand the masses of black holes and dynamics of objects around it by studying the light of things very near the event horizon and in its local environments. But as I said before, one of the early reasons to build the James Webb Space Telescope was to look back in time and see galaxies at the very earliest era of formation. In this funny, strange plot, we are here today where the James Webb Space Telescope icon is at the lower left hand of this funny cube. And as we go back in time, we are seeing objects that are more distant, earlier in the early history of the universe, and light that is redshifted into the infrared part of the spectrum. The beginning point we refer to as the Big Bang, and this early radiation-dominated era when there weren't even particles and normal matter as we like to think of it. And then something we refer to as the Dark Ages, where no light from that epoch can really escape towards us. When those hydrogen atoms that were formed finally ionized, then we can see the light because it's not obscured from our vision. And the first galaxies and first black holes formed, and the whole history of galaxies like our own Milky Way. How did they form, and how did we get again to where we are today? The story of our origins in planets, in stars, and in galaxies and the universe. These are questions that the James Webb Space Telescope will make large steps forward in our understanding. Gravitational lensing is another area where the James Webb will excel. I'll just draw your attention to this lower cartoon. If you have a very distant background galaxy like this red object on the far left, and in between you, say halfway in between you and a distant galaxy is a very massive object, then the light from the very distant galaxy is bent and focused for you, as though this giant galaxy in between is acting like a giant cosmic telescope, and it's allowing you to see objects even more distant into the early history of the universe than the James Webb could see, and it is magnifying the images and giving you unique insights into the early formation of stars and galaxies. So gravitational lensing is kind of us cheating the system, if you will, using the gravitational bending of light as another one of nature's own telescopes. And this is a remarkable example of that, where the light from the background galaxy has been stretched out all the way into a ring, filling the Einstein radius around that distant object. And in the middle, you see the lens itself, this giant mass of gravity, which is bending that light into this funny circular shape. And then we can analyze that light to understand the physics and chemistry of early star and galaxy formation. So James Webb is not the end of what NASA and the international space astronomy community wants to do. In fact, we have just received from the National Academy of Sciences, commissioned by Congress, our decadal survey of astronomy and astrophysics. This is the National Academy has been asked to engage the entire community and develop a report that should shape the policies of funding agencies like the National Science Foundation, the Department of Energy, and NASA for the next decade. And we've been studying many mission concepts, and James Webb is really going to teach us so much about what we need to know to build the next generation of facilities. WFIRST, or the Roman Space Telescope, named after Nancy Grace Roman, should be launched later this decade. And the new thing that we all hope to be working towards is an even bigger version of a space telescope, something in the middle of designs called HABEX and LUVOIR, which might have the capacity to take pictures of Earth-like planets around sun-like stars and look for signatures of habitable atmospheric gases in the planets of those stars. And then on the far left in the bottom is a really future concept of a mid-infrared free-flying interferometer, which will allow us to look at the emission of those planets, not just to see them in reflected light. And my colleagues here at Arizona or here at Michigan are working on studying early technological hurdles to overcome them for even those future missions. Well, that's more than what I wanted to tell you today. I apologize for going a few minutes over. We are all extremely excited about the launch of James Webb, and indeed, fingers crossed, it'll happen on the 24th. It could get delayed by a day or two. They will not launch it on December 25th, but there are windows every day up through about January 6th, about 30 minutes each day. Then we need to take a week off because the moon, believe it or not, would be in the way. And about on January 13th, more launch windows will open up every day. So sometime in the next week or two or three, the James Webb Space Telescope will launch, and we can't wait to find out what it'll show us. Please feel free to take a look at this web.nasa.gov link if you wish to know more. And thank you very much for joining us today.
All right. Well, thank you very much. And it will continue answering questions in the chat window if you'd like to post any more. And I want to thank you, Dr. Meyer, for such a fascinating presentation. So we'll look forward to your questions. And of course, we will be continuing to put more information out through our own programming at the planetarium, and hopefully even some more virtual events and even live events, we hope, as we go through the winter and spring, because it is going to be probably a good 6 months or so before all of the instruments have been calibrated and tested. But it's a very exciting time, and we all have lumps in our throats and excited at the same time. So again, we thank you all for tuning in and hope to see you in a future program. Thanks very much.